Thank you for joining this webinar from the Engineering Integrity Society. I will now hand you over to today's host, David Enzer, for an introduction to today's presentation.
Hi there, welcome everybody. This is the first lecture in our Removing Doubt and Uncertainty set of webinars. This one is Gaining Traction, Engineering in the Face of Uncertainty, Lessons from the World Rally Car by Damian Harty. Right, a little bit about us. This is Engineering Integrity Society. This is part of the Simulation and Testing Measurements group, but we have a series of groups: Durability and Fatigue, Sound, Vibration, and the Young Engineers Forum. We're a group of engineers that have been together for quite some time now, and we try to review what's going on in the general world of engineering. Next slide, please, Sarah. We are a charity, and we have a lot of corporate members who look after us. There's a list down there. You probably recognise a lot of them. I used to work for Hariba Myra, and there's even more of them. There's a lot of people that are behind us and actually support us. This series of webinars says about removing uncertainty. I'm looking forward to this first, because it's a subject quite close to my heart. Is actually being sure that not only do we collect data and work with data and analyse data, that we also make sure that we actually know what we're doing with it. It's the most important thing. In other words, how do we know we have a right answer? What do we do with it when we've got it? How do we set about setting up tests and so on? And there's a series of webinars covering a whole load of things by the EIS. Coming up soon is non-contact vibration measurement, reducing data and uncertainty measurements, which is ours. And also we've got a Young Engineers Forum webinar, is how to crash an efficient lightweight structure thousands of times and survive. So that's quite a good one. So anyway, coming on to today's presentation. This is by Damian Harty. I'm looking forward to this one to see what Damian's take is on this subject of removing doubt. David and I have talked about these sort of things for many, many years. We've known each other for a long time. And Damian's background is that he's a very experienced engineer. He's now a technical director at RE, but he's gone through most electric vehicle companies like Byton, Lucid, Tesla as directors or head of dynamics. Polaris as well. He was a lecturer and director at Coventry University on dynamics. And I've known him all the way back to things like ProDrive, SDRC, at Ford, where he's a CAE engineer, and at Encode, which is now Princia, where I used to work, and back then he was training and coming out of being a graduate. So I've known him for a long time, very interesting guy. I'll hand you over to him now. Thanks very much.
Thanks, David. Your words are very kind in introducing me. I put my camera on because I'm quite prone to waving my hands as I talk, but if it gives us any bandwidth problems, I'll kill it as we go forward. Without further ado, I'm just going to turn on the screen sharing, which I think should all have gone live now. You should be looking at the title page. This was taken by me standing in a ditch as Danny Sordo hurtled by sideways, and you can see I was pretty close to the action. This was one of the test days. A lot of people ask me about the toilet roll holder strapped to the front bumper. That's actually a Doppler radar for reading ground speed that we were allowed to run on test days, but you're not allowed to run it on event because it might give you a traction control advantage. So I'm going to talk about rally, and I haven't got any kind of special themes for reducing uncertainty in this first lecture, but I'm going to talk a lot about living beside it. That's the sort of main thing today. I've got four chunks. For those of you who are not familiar with World Rally, I'm going to talk a little bit about kind of what it is and how it's structured. The rules have changed slightly since I was involved in it, but the changes are mostly about powertrain changes. The sort of principles of what I'm talking about remain the same. Then I'm going to talk a little bit about engineering for performance in the World Rally environment. I'm going to talk quite generically, and then about some specifics on the mini WRC program I was very heavily involved in. And from those, I'm going to try and distill some general principles. My goal is to talk for sort of roughly 40 minutes, so until about 1:45, and then hopefully I've said some things that are interesting enough that will generate some questions as we go, questions at the end. My goal is to get interesting questions. If there's no interesting questions, then I'll feel like I've failed. So I'll jump in pretty quickly. The World Rally environment. The first thing to say is that an individual event is fantastically complex from a driver's point of view. A typical Formula One race involves going around the same 10 bends again and again and again. And for sure, there are variations like, the fuel loads change and the tyres wear out. But there's basically more bends in a single WRC event than there is in an entire season of Formula One. And the speeds are much slower, but the trees are much nearer to make up for that. It tends to be unrehearsed and really quite unpredictable. On Tuesday, the crews are allowed to drive round the stages. The stages are typically run on public roads which are closed for the event, but on the Tuesday they're still public roads, so they just get to drive like ordinary members of the public, and on Tuesday they get to have a look at everything and see if anything's changed since last year, or if this is a new stage, then they get to make some notes, and the driver will talk about the sorts of things that he'll be looking at when he's driving at event pace, and the co-driver makes notes as they drive round, and the co-driver transcribes those notes into this shorthand that you see on the pad, and it's slightly strange. There's a lot of symbols. It's very big. All of this is designed so that he or she can still read it while the rally car is being driven at pace. And when you sit inside the rally car being driven at pace, the ride environment is it's not particularly comfortable, and so you need this kind of big writing, and you need to hold the pad up to kind of keep it still so that you can read it. And this sort of shorthand, all the drivers and co-drivers use their own shorthand. There's no kind of internationally agreed standard. But they typically talk about distances and speeds. There's sort of some sense of speed. It's not very well defined, but they kind of talk about, Chris and Paul used to talk about kind of fifth gear, fourth gear, third gear, and that gives them an idea of the bend. And the idea is to stop them misreading the bend that they're coming up to. And then they also make notes, and so they've got, an exclamation mark means caution, and the little kind of less than sign means that it tightens into the bend. And so these are the sorts of things that you hear the co-driver saying, and they'll say things like 80 into 5 right, over crest into 4 left, tightens, caution, or something like that. You'll hear them talking this very sort of terse vocabulary, and they normally sound like they're working fairly hard to speak, because the ride environment is quite aggressive and they're quite strapped in. So it's an interesting event in terms of driving, because it means the idea that you're somehow going to drive the perfect speed through the corner is not possible, because there's too much that's unknown. So what you've got to do is sort of sail close to the wind, and the event winner is the driver who can sail closest to the wind without falling off the road. So it is a kind of a slightly different game to circuit racing. In terms of the environment that it presents to the car, there's sort of two big chunks really. By far the most numerous is the gravel environment, and depending on where in the world they're run, they can be at quite high ambient temperatures. For a typical gravel environment, there's continuous inputs up to about 2.5 meters per second on the in terms of the wheel travel going up and down over bumps. And to give you some sense of what that means, when a road car drives up a curb, somewhat rudely, you get a kind of 1.5 metre per second input. And for normal driving on a motorway, you're down at sort of 0.1, 0.2 metre per second input. So it's a really aggressive ride environment. And it works the dampers very, very hard. The thermal behaviour of the dampers is really quite important. It's a key performance limiter. And particularly at the rear of the car, it's difficult to get air to the dampers because the brakes are getting even hotter. I don't know how well it will show on your screen, but the top right picture is one of the mini wheels with the disc glowing the sort of dull red, and this is just in daylight after it's come off the end of the test stage, so the discs have really been very hot. So what that means is there are quite big challenges to keeping the wheel in contact with the surface. And if you look at the sort of damper velocity versus travel trace, it has this very characteristic looping character with a sort of a slope down the left-hand flank. And the slope down the left-hand flank is characteristic of the wheel being in free fall and not in contact with the road. You typically don't see shapes like that when a car is fully in contact with the road. So there's a lot of bumps basically. The other type of event, which is far less numerous than the gravel event, is a tarmac event. They tend to be somewhat smoother than the gravel events, although they're still quite rough by road car standards because they tend to be on sort of disused back roads rather than main roads. They also tend to be quite tight little roads, and so funnily enough, the tarmac roads, the speeds tend to be tarmac rallies, the speeds tend to be lower than the gravel rally, and there's a lot of compromise. You'll see the rally drivers basically putting the wheels into a ditch inside the corner, and they hook the car around the corner a little bit like a scale electric car. But you have to be quite careful doing that because at the end of the cut, if you don't drive out of the cut in a nice controlled way, if you just get to the end of the ditch, then it will just flip the car over. It's an overwhelming vertical input. So the driver has to be very careful when they're cutting because of this cut exit, and we have to be very careful when we're engineering the end of travel performance because otherwise we'll loft the car onto its roof. The ride height tends to be a lot lower. It tends to be about 100 millimetres lower, 4 inches lower. So visually, the cars look very different between gravel and tarmac, and that's because we want to lower the CG height and reduce the weight transfer. But really, even though it's a fairly conventional car, tarmac car, there's still a lot of sophistication in the end of travel performance. And then on top of those, there's some wild cards about rallying. Everybody likes to see the cars jumping in Finland. The drivers try not to jump too high, actually. They try to carry speed through the jump. But whenever they're in the air, they can't be driving or braking, and so it actually limits the performance. So they try and minimise the amount the car jumps. It's also very important, they have a surprising amount of pitch control over the car by using the brakes and the accelerator pedal, just reacting against the wheel inertias. And it's quite important that they don't put the car nose down when they land. It puts very big loads on the front suspension, so they try and basically kind of keep their foot in a little bit to pitch the car up a little bit, nose up a little bit, not too much so that it goes all the way over, but just a little bit so that it puts the rear wheels down first, fractionally, and kind of lands fairly flat. There's lots of issues managing tyre temperature, where sort of Formula 1 cars are going round and around and around on the same track. The rally cars are being dunked in water, or they're perhaps running on snow. And if you look at an event like Monte Carlo, they're running between tarmac and ice, and that can be really quite difficult. There's always some kind of trade-off between the sort of absolute performance of the car and the confidence that it gives the driver, and typically you give away a little bit of performance to give the driver confidence. And then finally, we do our best to make the cars very sturdy, but there'll always be a bigger rock. And so there'll always be some kind of event that can overwhelm the suspension and pull the wheel off. And you frequently see rally cars with wheels pulled off. There's some very famous footage of Sebastian Loeb driving with his co-driver hung out of the window to make up for the fact that one of the wheels has come off, and just try and stop putting that corner down on the floor. But in the end, we try and design them for a certain size rock, I'll say, and then we ask the drivers to drive round rocks that are bigger than that. And that's always an interesting conversation if the drivers have not driven around a big rock and the wheel has come off. But there's an interesting conversation between the engineers and the driver about why wasn't your car stronger, why didn't you drive around it? Because obviously if you do pull the wheel off, it generally retires you from the rally. And so in terms of time penalty, it's sort of infinite. So that hopefully gives you a sense of the task that the vehicle has to perform. It's not that dissimilar to the task that military vehicles have to perform, in that it's a little bit chaotic, it's a little bit undefined, and it's performed at speed. The difference with the military vehicles is you throw in the fact that you've got people shooting at you, and you've got 18-year-olds who don't get paid very much and don't own the vehicle, so that makes military vehicle engineering even more difficult from my point of view. So that hopefully gives you a sense of the kind of rally environment. And as you can see from this picture, the drivers are not always constrained to what look like the road to us. They can be really quite creative with some of the lines and directions that they choose. And there are very few rules about how they actually negotiate the stage. So now I'm going to talk about this as an engineering task, because at the moment it all just looks like total chaos. The formula itself means that the engines, this information is a little bit out of date now, but for the principle is that the baseline performances are given. And there's a goal in the rules that tries to equalise the engine performance, really. And so when I was working on the rally cars, there was a restrictor, and you can get per millimetre squared of restrictor area, you can get about 270 watts out of a good internal combustion engine if you can blow the air through it fast enough. So the job of the turbocharger was to force the restrictor into saturation. The fuel that you can use was controlled. You couldn't use anything special or exotic. And for some of the years that I was involved, the tyres were also set tyres. But for other years, there was a kind of a tyre battle between Pirelli and Michelin. The weight is very strongly controlled. You're not allowed to engineer a car that is lighter than 1,200 kilograms without the crew at the stage end. And because of the uncertainty of fuel load, we typically set it a little bit higher than that. We typically set it about 1,230 kilograms at stage end was what we were shooting for. And then if we used 5 or 10 litres more of fuel than we intended to, we had a little bit of headroom there. And the aerodynamic performance tends to be dominated by the base car. The rules for WRC have changed over the years, and the cars are getting more and more aggressive. They're looking more like Pikes Peak cars, but they're still, you're not really allowed to do anything hugely radical. And so when we come to this sort of baseline performance, and quite a lot of the time the baseline is the previous year's car, what we're trying to do is subtract time, really, and we're trying to change things, and we can write it down as a sort of partial derivative summation here. We're trying to look at what we can change and how much we can change it by. And if we had an infinite amount of time and resource, I'm pretty sure that we could come up with some optimum that couldn't be improved. But in the real world, what we're actually trying to do is make the most change that we can in the time available. And that's the art of motorsport engineering, really. And an important trick in that is to recognise the difference between what I'm calling primary factors and hygiene factors. If it's a primary factor, then if you make it better, the car gets better. And notwithstanding the rules, mass is a good example of that. If you just keep making the vehicle lighter and lighter, then for a given power output, it will accelerate better and better, and there isn't any limit to that. These hygiene factors, if you get them wrong, they'll slow the car down. But if you get them right enough, then spending any more time on them doesn't make any difference to vehicle performance. And the example I always use, you'll see that the headsets are built into the helmets when the drivers are driving, and the co-driver obviously has to talk to read these pace notes to the driver. If the headset volume is low and the driver can't hear the co-driver, then the driver has to slow down and drive visually, and has to be much more conservative so that the vehicle doesn't leave the road. And so it seems at that point, if you start from an intercom that has a too low a volume, it seems that if you improve the volume on the intercom, the car goes faster, and that is true. But once the intercom is loud enough, then making it louder doesn't help. And so once you've got the intercom loud enough, you should stop talking about and thinking about the intercom volume, and you should move on to something else. And that's really the key difference between primary and hygiene factors. Is what you're trying to do with the hygiene factors is put them in the right place and then walk away from them and never talk about them again, because resources are very limited. So when we look at all sorts of things, and I'll come back to some of the information in this slide later. But if we're systematic enough, we can think about what we're doing, and we can set some priorities. And so one of the things that we can prioritise, it's fairly obvious from a motorsport car, is the CG height. Another one, because the surface is so bumpy, the unsprung mass is very important. And then any aero forces we can get are an improvement, bearing in mind the limitations of the rules. And obviously, if we can trim excess mass, that's very helpful. And excess mass is a funny thing. If you look at the vehicle in the picture at the bottom left, that's a test stage in France. I can't remember where exactly in France. And the mud it had a very sort of clay quality to it. And your feet got heavier as you walked around with the mud that accumulated on your feet. And the car will accumulate something like 100 kilograms of mud on it during a stage distance. And so it starts to become interesting to mask areas with little sort of mylar sheets and cable ties to prevent mud going into cavities and accumulating. And the cost of the sort of weight of those components is actually offset by the fact that they stop you accumulating mud. And of course, you can't really rely on it to make a lightweight car, because there's a sort of a somewhat likely occurrence of a critical piece of mud dropping off the car just before it goes to be weighed at the end of the stage. So there's some curious things like that. Those things on the left-hand list, the design list, if you get them wrong, you basically have to wait until next year to get them right. That's maybe, it's not true for all of them, but certainly for the CG height, you can't just bolt in a lower CG. You have to do a lot of work to meaningfully lower the CG height. So the design priorities tend to be the ones that are hardest to change and take the longest to change. The development areas tend to be things that yield benefits now, and that you can kind of slot into the car. And so some of them are things like details of oil scavenge pumps in the engine, to reduce some of the parasitic losses in the engine and get more of the net curve out of the engine and down to the ground. Some of them are aero changes that again are relatively simple to bolt on, although there's limits to how much you can change event to event. But really a big one is grip, the amount that you can persuade the tyre to interact with the surface. And typically the features that do that, you have got quite a lot of freedom with. And because the motion of the car is really the sum of the forces between the wheels and the ground, that becomes very important. So to kind of step back a bit and look at a typical kind of 5-year program for a base design before there's a really major redesign. We kind of start off at 100% performance, let's say, and we're looking to add about 1% a year to that level of performance, which doesn't sound very much, but the truth is, hopefully, you made a good job on day one, and so there's no low-hanging fruit. And all the other teams are doing their best to improve this as well. And a big part of the task is really the sort of underlying performance, which is things like weight distribution, CG height, all of that stuff, and all of those hygiene details that if you get them wrong will slow the car down. And that's by far the biggest. I talk about that being kind of 97% of the job. The numbers are not really very exact, but you get the idea. And then there's a few things that deliver the sort of the final 3%, I'll say, which is broadly the difference between first and fifth place over 350 kilometres, about 1 second per kilometre. And that's the kind of hygiene factors that you've got to get right to encourage the driver on the day. And so they're things like the handling balance of the car for this particular event, the ride height of the car for this particular event, that sort of thing. And typically there's only a certain kind of bandwidth of those. It's difficult to make that band grow over years. So over year on year. So what you're trying to do is improve the kind of underlying performance. And so what you want is a somewhat lengthy program to work on engine power with primary changes to the engine rather than detailed changes to peripherals, and also typically the sort of mass weight distribution and CG on. So that's a kind of a sense of what we're trying to do, and the main thing to take away from this is really how small the percentages are that we're looking for. We talk about a meaningful difference being 0.1 of a second per kilometre, so you can see that that's a kind of 0.3% difference. And in the face of all this chaos that we saw, it's actually quite difficult to work out whether you've really made a 0.3% difference or not. So that's I'll say a large and a small view of the sort of overall task for engineering performance. So now what I'm going to talk about a little bit is the specific journey that we went through on the Mini WRC. And the reason that the Mini WRC was really interesting was when Subaru exited, ProDrive didn't have a contract immediately with another manufacturer. But rather than sit and wait, we said, let's pretend we've got a contract with a manufacturer, and now think about what rally car would we want to engineer. And there was a huge amount of effort went into many things of kind of getting ourselves organised. And one of the ones that I picked up was this idea of really systematically prioritising engineering for performance. Because when your resources are limited, the ability to prioritise accurately is what sets apart one group of people from another. So the first task was to chop up the kind of stage event, if you like, into pieces. And typically there's a launch from standstill, and then there's a whole sequence of brake, turn in, mid-corner, corner exit, drive out of the corner, repeat. And the corners are bigger and smaller, and so on the bottom of the slide there you can see a sort of, this is actually a short circuit speed trace. I haven't got any rally speed traces to hand. But you can see the speed goes up and down as the corners get bigger and smaller. And you can see that characteristically the speed trace, and this is common for most things, the speed trace is much steeper under braking than it is under drive. It's only at the lowest speeds that you can get as much drive as you can braking. As soon as the speeds come up, with finite power, you start to dissipate power into the wake, and you haven't got as much power to put down to accelerate the car. So the speed trace always has this characteristic sort of climb to flat to Vmax. Rally cars are almost never running at Vmax. They're pretty much never power limited. They're almost always either limited by the availability of space, and quite often there's trees very close to the road, or the kind of radius or the surface friction. There's usually something other than power limiting the cars, which is why the flat power curve isn't actually that much of a limitation. The current generation of rally cars are mostly as fast as the Group B cars ever were, because they've got a lot of area under the power curve, whereas the Group B cars had a very sort of traditional power curve that climbed up from low RPM to a peak. And so the goal was to kind of split the behaviour into these different phases, and to try and identify which one had the most potential. And the interesting thing is, for launch, you can say, well, that's not really going to move the needle very much, because it's only the first 5 or 10 seconds of a 20-minute stage. So even if you doubled the launch performance, you can't make much of an improvement. Whereas if you look at that speed trace and imagine lifting the bottom of each of those loops by 1 kilometre per hour, you basically lift the entire speed trace by 1 kilometre per hour. And given that the average speed for a World Rally Car event is 100 kilometres an hour, then 1 kilometre corner speed, presuming you can do it everywhere in the speed trace, is basically 1%. And we talked about 3% being the difference between first and fifth. So 1% is a really meaningful increment to chase. Braking and corner exit, they have some influence, but to be honest, because you're not braking all the time, and you're not driving out of the corner all the time, they have less influence in mid-corner. And the influence of turning is interesting, because when you talk to the drivers, they're very interested in the ability of the car to follow the wheel, and it manipulates their confidence a lot. And if you've got a car that won't follow the steering wheel, then it can dent their confidence quite a lot. There's a very famous article about Ayrton Senna driving rally cars the first time he drove them, and basically understeering off the first corner, and how it really put him off. And to start with, he was really quite slow until, of course, he's Ayrton Senna, so within an hour or so he'd learned what was going on and was faster than anyone else. But the point is that the turning can be quite difficult to quantify. So because of that, we just parked it. We said, well, we kind of, we can play games with the subject to try and comfort the driver. But from an engineering point of view, it's pretty obvious that the mid-corner performance is a very important one to chase. And so the next part of the task then, having identified that mid-corner is top of the list and traction is second on the list and so on, is to start working through what are the influences and effects that we can work on. And the mass distribution and CG height are big ones. We on the Mini, we felt that we were chasing a 50-50 weight distribution. It's interesting that Citroën don't do that, and I can't comment on that. It clearly means there's multiple solutions to the problem, shall we say. But the Subaru is typically quite nose heavy. It's quite difficult because the boxer engine is quite stubby, and the arrangement of the transmission forces the engine to be ahead of the wheels. It was quite difficult to make the Subaru 50-50. So anything that you could do to even up the weight distribution would help the vehicle performance, and anything that would lower the CG would help the vehicle performance. And when you looked at the relative influence of those two, we ended up with this kind of golden vector of 8 degrees from the vertical, and this was true only for the Subaru. where whenever we wanted to move anything, that's the direction we should move it in, and we should identify all the heaviest bits and try and move them as far as we can along that vector. And that's a great design rule to just give to component engineers and designers, because you can just say, the heavier it is, the more I want you to move it down that vector, wherever it is in the car. And they can do that without needing an overall knowledge of where everything else is. So that was a really kind of liberating and simple conclusion to draw. The next one that's very important is the wheel load management, and I'll come on to talk about that, and so on. And so we went down all of these things that we felt could influence these items, and we worked down them and identified their influence with relatively simple models in order to shift them into priority order. And the priority order is, again, it's really the key when the resources are limited. And so we were able to produce a table a bit like this, where we said, if we really want to meaningfully change the CG height of the vehicle, it's a 1,200 kilogram vehicle. To move the CG height 20 millimeters is a big task for a given ride height. And so really we're looking at re-engineering the vehicle, and that's kind of 10,000 hours, if you like. These numbers are all very nominal, but they give you a sort of a sense. If we wanted to get aero force benefits, there was typically quite a lot of elaborate work on them, because it was a lot of trial and error using CFD of, we'll try this, we'll try this, we'll try this. So there was a lot of time developing shapes, and the CFD runs are quite long. And then we would make some prototype parts and perhaps compare some candidates against each other. So that was also quite long. In order to really move the needle in terms of unsprung mass, we were looking at some quite big changes, because the unsprung mass was about 45 kilos. So if we wanted to make a tenth of a second per kilometre change, we were looking at taking 10 kilos out, which is sort of, an entire brake disc or an entire brake caliper. And that's not a thing to do trivially, so there's a lot of work in that. And then we could kind of work down the table. And so you can see that from top to bottom is really the design priorities, because it's important that you get them right when you're engineering the car, the baseline car, because you don't really get the opportunity to loop back. And then from bottom to top are really the development priorities, and that's where some of the information in one of the earlier slides came from. And all of these numbers they're not very exact, but they are kind of honest best guesses using relatively simple models that allow us to meaningfully rank things, because otherwise one person is very keen on reducing unsprung mass, and another person is very keen on changing the weight distribution, and there's a whole load of swirl and churn between what gets actually worked on, and people end up chasing pet theories, whereas this table is a great tool to say these are the priorities. And so once we'd identified the priorities, then the next task is to actually focus some resources on them, and this is where people kind of recognize really what's going on. I apologize for the formatting that's gone slightly wrong on my sketch there. There's a bonus prize for anyone who can identify the error in the diagram in the algebra on the right there. The key with this activity is to not try and make a perfect model. You need to make the most useful model in the time available, and just get over the fact that it's wrong. So this algebraic description on the right, it's a great way of describing what the model is. But the model we actually use, it can loft. So there's a nonlinearity in all of the forces, the wheel forces, so that it can jump and land. The characteristics are nonlinear, so we used numerical methods rather than the sort of classic algebraic methods. I just used the algebra to basically formulate the terms, if you like, in the numerical model, but it's not a linear model that's being run to draw the conclusions. And some of the conclusions that came out of this activity were really quite interesting, and quite a few of them were not that obvious when I started the activity. So the first one is the vehicle corners don't really know about each other. So I didn't need to do this 7-degree freedom model. I could have just done a 2-degree freedom model and drawn all the same conclusions. But I didn't know that until I'd done both and realised that they both produced basically the same answers. The other one that's very interesting is that provided that you're not running out of travel, the optimization for load variation in particular, which is a good surrogate for grip, you don't need to know much about the surface. If it's got the kind of, the right amount of energy in the surface profile, then you'll draw the right conclusions about the characteristics that you're chasing. And that was a massive one because it freed us from worrying about the difference between Turkish gravel and Spanish gravel, for example. And the other thing is that there are actually many, I'll call them equivalently optimal damper characteristics. So you can tune the dampers in particular to give you other things, the sort of sensation of confidence that the driver has after a jump, whether the vehicle climbs in ride height over a rough surface or whether it sinks in ride height over a rough surface, and so on. And so this problem was very well suited with numerical methods, very well suited to a sort of numerical optimization methods. And I won't bore you with too many details, but some of the things that came out, there was a lot of data that came out, and it caused us to draw various conclusions, and it drove certain qualities into the dampers, which were really interesting. And so the kind of, the question is, did it work? And the first tarmac event for the car was in France, and Danny Sordo was only 8 seconds behind Sebastian Ogier. He was in second place, and 8 seconds over 350 kilometres is next to nothing. And so it's clear that the base performance of the car was really very good. Luck can make a good car slow, but luck doesn't make a bad car fast. So it's clear for me that this was some kind of measure of the underlying performance of the car. The team founded for sponsorship issues basically, but it felt to me like all the science we'd applied was good, and the performance of the car was good. It was notably lighter on its tyres compared to the preceding Subarus, so we could typically run 1 compound softer on the tyres compared to what we would have run on a given event in the Subaru, even though the vehicles were the same weight and had the same power output. So for me, this was a kind of a big endorsement of the car. So finally then, my last slide is kind of so what. After talking about all of this, so what? So these were some of the things that I took from all of this work on the rally car. And in fact, the first one is a very generic thing that I identified very early on in motorsport. If you guess everything, it's very, very fast. And the risk, of course, is that it's a guess and that it's wrong. But you can develop your ability to guess over time and calibrate your guessing. And so it gets less frightening than it seems to guess a lot of things. You definitely need to know what success looks like. If you don't know what success looks like, then you're never going to get there. And then the next 2 points sort of tie together really. You've got to be able to kind of mechanistically describe what's going on with the thing that you're engineering. And if you can do that, then you can go back to your guesses and you can work out which guesses are important that they're right and which guesses are not important that they're right. And what that means is that you can prioritise things. And the key to success in the face of uncertainty is working on the right things and having time to work on it. So the golden principle for me is to never, ever, ever wait for data. When anyone says, we'll have to wait for that to be measured, I turn on my heel and walk away and carry on doing something else. I'll use the data when it becomes available and compare it to the guesses and the predictions that I've made, but I'll never defer a decision to data unless it's something really extraordinary. And then my final point really is that there is a class of things that you'll never be able to predict, and you need to identify that and just kind of make peace with it. And the weather, of course, is a perfect example. We know that it'll rain in November, but we can't say whether at 1:45 on November the 16th, 2023, whether it will be raining or not. That's just not on the cards. It's never been on the cards. It will never be on the cards. And so we need to understand that there are some things that we can't predict. So hopefully that made some kind of sense. Yeah, I'm happy to. It's 1:45, maybe a minute after, so I'm pretty much on time. We've got time for any questions if anyone's got any.
Thanks, Damian. That's really, really good. The one thing I got from that, actually, it seems very important to be sure of what you have right at the beginning of anything, and to prioritise what's actually there as opposed to what people think is there.
Yeah, absolutely.
In actual fact, I don't suppose that, but a lot of that seems very reminiscent of that paper you did some time ago of usefulness. Seems to come in there quite a bit.
Yeah.
One thing I like, Damien, is I did like your use of what is effectively Paretoing things, so you actually get an idea of what really is important to concentrate on as opposed to what you guess is or what people's preconceived concepts are.
Yeah, and I think that's why it's important to have a kind of I'll call it a mechanistic understanding, because what you want to be able to do is to run the model, whatever that looks like, but do it kind of blind and in a sort of a neutral way, so that the model can talk to you about what's important, rather than you just presuming something's important. So, for example, the idea of the kind of mid-corner acceleration being important, lateral acceleration, it's well known that it is on the circuit, but it wasn't at all obvious to me whether it was or wasn't on the rally car. And so I was able to take a load of GPS data and then calculating on a kind of data by data point, what if we wound up the lateral acceleration by this amount, and make a new speed trace, if you like, and take a time delta, and that returned the same answer, and that was very helpful from quite a simple data set to be able to draw that conclusion. And that was a robust conclusion over multiple different stages. And so by the time I'd done 6 or 7 of them, I thought, okay, it's time to accept that it is just the same as any other form of motorsport, and the corner speed was really helpful.
We've had a question come in, Damian. How much do you allow for the driver? Consistent versus erratic? Is the best driver consistent?
That's a question that kind of will run and run. So early in Colin McRae's career, he had a reputation for either being really fast or crashing, and there was no middle ground. And of course, there's a connection between the two, because nearly too fast is very, very similar to really too fast. And so the consistent drivers tend to always bring the vehicle home. But the whole art of rallying is working out how close you can get. And it's interesting as well that the rallying is really demanding from a kind of visual processing and everything else point of view, and so it's really fatiguing, and it's really easy after 20 minutes of driving like this. If you've ever done a track day session, you'll know that you sort of get a bit mesmerized after 20 minutes. When you're driving like this in an unrehearsed way, it's really easy to make a mistake on the kind of second to last bend and throw it all away. And so the driver's ability to kind of retain focus and retain concentration becomes something that really differentiates the drivers one from another. And so there's not much we can do as engineers other than try and make the car so that it's not any kind of knife edge, so that it doesn't reward or doesn't punish rather an input that is slightly wrong, but there's a big sort of plateau of performance that gives the driver an opportunity to collect up the car if they make an error. It's very unlike circuit cars where there is quite a knife edge and you fall off a cliff very fast. As soon as the car, particularly on cars with a lot of aero, as soon as the car starts to rotate, the wings stop working, and at that point you're going way, way, way too fast. So it's about making the plateau, which is of course a different task to the circuit optimization task. I hope that answered the question.
I did like your comments about the mud build-up, Damien. That's a very interesting one. It can also cover for road cars, I suppose, as well.
It can, yeah. And enduro bikes and kind of anything that goes near mud. It can be a surprising modifier.
Coming back to the driver thing, I suppose it's the fine balance between the fact that to be able to finish first you have to finish, which I think is a quote from...
Indeed, yeah.
But I suppose the other one is that, well, at least finish well up or finish first in as many of them as you can. It's another thing.
Yeah, and I think to go back to McRae, he when he didn't crash, he did win, and so people were quite forgiving. And then he basically learned that you could sort of turn the wick down to kind of to 99%, let's say, and still be first, but crash far less often. And that once he got to grips with that, which is a very sort of personal thing that a driver has to learn. Once he got to grips with that, then he became really a dominant force.
I think one of the things for the theme of this whole series of the seminar is the one thing that I did like that I picked up from your lecture is to end up with some sort of good idea of what you're trying to measure, what you're trying to do. And the one thing I picked up was this thing of it was the time stage, the seconds per kilometre gain.
Yeah.
If you've got something like that as a goal, it's very easy then to prioritise what you're trying to do because you've got a really clear idea of what it is you're trying to do.
Yeah, and that is actually, I think, is one of the things that makes motorsport easier than other things, because success is time, either lap time or stage time. Whereas if you're making a Nissan Qashqai and nobody's ever made a car in that segment before, it's difficult to pin down what success is. And yet that car was a runaway success. It invented a new segment.
Yeah. If it was easy, we'd all be doing it.
Yeah.
But I think that is very important, actually, is that it's one of the things that I noticed both when we were working together as Encode and when I worked very much at Mira over many years, is the amount of time people will just come across a vehicle, they say we've got a particular problem or just a development program, let's go and collect some data.
Yeah.
And we'll work with that data afterwards. It never, ever works.
Yeah.
Just collecting data for data's sake is of no use. You need a goal, you need to know why you're collecting it, and you need to do completely the other way around. What you did here, I think, was excellent. It didn't really matter what car you started with. You know what the parameters are to measure another car later on.
Yeah.
So we've had a question come in. Have I understood the beginning of the process you outlined? If you are dealing with a problem completely unknown to you, the process is to guess, build models, verify understanding of the mechanisms, and then understand your guesses better? Or should the time be put into understanding the mechanism first?
So I feel like there's a little bit of both. If it's really unknown, you're trying to sort of bootstrap yourself a little bit, and so a combination of different guesses is the method that I'm espousing. And interestingly, I read a book by the physics guy who used to be a pop musician, whose name I can't remember now, who's ultra famous. a British guy, and he talks about this process of you kind of guess something and you put a model together and you try it and you see if it produces something like plausible results for something that you've already observed. And if it does, you say, well, that passes the sniff test. Let's pretend it's true and work with it. And in the meantime, we'll start worrying about whether it's true and developing the model further. But that kind of bootstrapping your way in, jumping in with a guess at values for things and a guess at the mechanisms that are in play, that's a key part of the process. It's kind of not being afraid to make that first guess.
Did you mean Brian Cox?
Brian Cox is exactly who I meant. Yeah. At my age, I struggle with names. Just go away from me. It's driving me mad.
You're still young yet.
I'm 150 in my head though.
I think that's true. I mean, I've made that point in quite a few other presentations before. Actually, there's an it's an unfortunate thing for people that like to collect data and just do a lot of work, is that you can't beat a guess.
Yeah.
If you guess correctly, it's the fastest way to a solution.
Yeah.
If you guess incorrectly and are then not prepared to guess again or change your mind or Pareto it as you have here, sticking with a bad guess is the longest and the worst way to try and go to solve any particular problem.
Yeah, absolutely. Yeah.
I've obviously given them too much to think about there, Damian.
Yeah, I mean, from what I said at the start, this now is an abject failure for me because there are too few questions.
I don't think so. I think there's a lot to take in there, and it is very interesting what you've actually said, and it will take some engineers a lot to look at this type of approach and to say it's doing the work up front is what people find very difficult to do.
Yeah.
Especially in big organisations. Big organisations, very easy, just turn the handle,
Yeah.
do the same thing, and lo and behold, the car comes out at the end, and it's probably going to be okay on the road.
Yeah.
Until something goes wrong, or you suddenly change things and decide to build an electric vehicle.
Yeah.
And it's something you've never done before, and suddenly you can't just turn the handle and it comes out the other end. You have to understand some of the principles.
Yeah. Yeah.
And see where you're going. So you have to understand the problem first.
Yeah, and I think it's when something changes is what sorts the wheat from the chaff, really. The early in my career, I used to use the example of the Golf and the Renault Espace. You know, if you were just going to make another Golf, you looked at the last Golf and you just made it a little bit more. But the jump from a Renault 20 to a Renault Espace is enormous. And yet Renault made it with some aplomb and again invented a market segment that didn't previously exist. And so that's very impressive. And now as we look at alternative powertrains, it's an even bigger jump, and it's very interesting to work with a lot of those vehicles and to you can see who can think clearly and cleanly from first principles. And I'm not particularly a fan of Mr. Musk, but a lot of the people who work for him are very astute. And every conversation at Tesla would at some point go back to can we just sanity check this against first principles? And it was a great way of are we leading ourselves up a blind alley, or is this actually the thing to do?
I think that goes even more into things where you're talking about autonomy on vehicles.
Yeah.
Because there's nobody's bottomed that out yet as to what's really happening.
Yeah.
Certainly because you've got a driver mixed in the middle of it, which is very difficult. Okay, I think if there's no more questions, I think are we done then, Sarah?
Yes. Yep.
So please don't forget the rest of this seminar. There's quite a few more. This has been a very good introduction. It's brought in pretty well most of the principles that we're going to be talking about with the other presentations about uncertainty and how to get to clarity and how to actually come up with a sensible engineered solution as opposed to just the mess that most of life really is. I'll leave it to you to finish off then, Sarah.
Okay, well, thank you for joining us. I think most of you have registered for the next webinars, but if you just messaged me and said you just specifically wanted to join this one and you've now changed your mind, do let me know and I can add you to the list for future events. Thank you.
Thanks very much all. Thanks, Damian.
You're very welcome.